Hello and welcome! Today we are going on a mathematical treasure hunt. We're setting out to find all the solutions to polynomial equations. Not just the obvious ones you can see on a number line, but all the hidden ones too. Let's dive right in.
So think about this for a second. If you try to solve for x, you get x squared equals -1. And we've all been taught you can't take the square root of a negative number, right? It feels like a total dead end. But what if it's not the end of the road? What if it's just the edge of the map we've been using? We've got a really clear path laid out for us. We're going to start by finding the missing pieces of our math puzzle. Then we'll uncover a fundamental promise that guarantees we can find all the answers. After that, we'll learn how to spot these hidden pairs of solutions, and then we'll put it all to work with a step-by-step calculation. And finally, we'll see why any of this actually matters in the real world. Okay, so our first stop is to understand why our standard toolkit, the real number system, is sometimes incomplete. It's kind of like trying to finish a massive puzzle when you know for a fact some of the pieces are missing. This is that exact same equation from the beginning. On that familiar number line we all know, there is literally no number that, when you multiply it by itself, gives you -1, right? A positive times a positive is positive, and a negative times a negative is also positive. So working just within this system, we are totally and completely stuck. To find the answer, we have to expand our universe. We need to move from just the real number line to the complex number system. And in this bigger, more complete world, the square root of -1 actually has a name. Mathematicians call it I for the imaginary unit. And this one little invention, well, it unlocks everything. Now, once we have I in our toolkit, we get this incredibly powerful mathematical promise. It's a guarantee, really, that we will never hit a dead end again when we're trying to solve these kinds of equations. And this is it. This is the master key. It's called the fundamental theorem of algebra. And what it says is actually beautifully simple. Just look at the highest exponent in your polynomial. That number, its degree, tells you exactly how many roots or solutions that equation has in the complex number system. Not more, not less. Now, you might hear about counting multiplicity. That just means sometimes a root can show up more than once, but the grand total will always match the degree. So, for an equation like x to the fourth minus 625, the degree is 4. And this theorem guarantees us that there are precisely 4 solutions out there waiting to be found. 2 of them might be pretty easy to spot, but we know for a fact that all 4 exist. Our job is just to hunt them all down. So how do we find these other non-real roots? Well, it turns out they have a very predictable, very convenient behavior. They never, ever show up alone. I absolutely love this analogy. It just captures the idea so perfectly. You can find a single real root, like the number 5, all by itself. But complex roots are different. They always appear with a partner, like a perfect reflection in a mirror. This predictable behavior has a formal name. It's the complex conjugate theorem. And it says that as long as a polynomial has real coefficients, which just means there are no i's in the original equation itself, which is true for most problems we run into, then its complex roots have to come in these pairs. So if you find one complex root, say 3 plus 2i, you automatically know that its conjugate, 3 minus 2i, is also a root. It's a total 2-for-1 deal. Okay, now this is where the magic really happens. Let's just walk through this for a second. First, you take a conjugate pair and you write them out as factors. So you have x minus our first root and x minus our second root. When you multiply them together, and yeah, it takes a little bit of algebra, something pretty incredible happens. All the terms that have I in them perfectly cancel each other out. And what you're left with is a nice, clean quadratic factor with only real numbers. This is an absolutely crucial technique for breaking down bigger, scarier polynomials into smaller, manageable pieces. All right, enough theory. Let's roll up our sleeves and actually solve a problem from start to finish. This is where we're going to see how all these tools work together in harmony. Here's our challenge, the one we mentioned earlier. We know from the fundamental theorem that there have to be 4 roots. So let's go find every single one. First up, a really clever trick to make this whole thing simpler. Dealing with x to the 4th power can be a little intimidating, so we're going to use a technique called u substitution. We'll just temporarily replace x squared with a new variable. We'll call it u. And since x to the 4th is really just x squared squared, our big equation, x to the 4th minus 625, can be rewritten as a much friendlier quadratic, u squared minus 625. So much easier to work with. Now, u squared minus 625, that should look pretty familiar. It's a classic difference of squares. So we can factor it really easily into u minus 25 times u plus 25.
Now that we've factored it using u, it's time to substitute back. We just replace u with x squared again, and that gives us our two factors, x squared minus 25 and x squared plus 25.
Let's solve each of these factors now. The first part, x squared minus 25 equals 0, well, that's another difference of squares. Easy. That gives us two real roots, x equals 5 and x equals negative 5. Simple enough. Now for the second part, x squared plus 25 equals 0. This is where we find our hidden roots. If we subtract 25 from both sides, we get x squared equals negative 25. Now when we take the square root of both sides, we get x equals plus or minus the square root of negative 25. We can think of that as the square root of negative 1 times the square root of 25. And since we know the square root of negative 1 is I, and the square root of 25 is 5, our two complex roots are 5i and negative 5i. And look at that, a perfect conjugate pair just like the theorem predicted. And there they are, two real roots and one pair of complex conjugate roots. Exactly 4 solutions in total, just like the fundamental theorem of algebra promised us. We've solved the unsolvable.
So here's the crucial point. This isn't just some abstract mental exercise. Finding these roots, both the real and the complex ones, has incredibly important applications in the real world. Think about it like this. A polynomial can represent a company's profit, the path of a rocket, or the cost of manufacturing something. The roots, those are the points where that polynomial equals 0, they often represent the most critical values in that whole system. A 0 profit point is your break-even point. A 0 height point is where an object finally hits the ground. Just look at this simple profit model. If you produce 0 units, you have a loss of 15, probably from startup costs. If you produce 3 units, you're making a nice profit of 24. But right there, at 1.5 units, the profit is exactly 0. That's a root of the polynomial, and that is the critical break-even point that the business manager absolutely needs to know. And this idea, it extends everywhere. Businesses use this for profitability analysis. Manufacturers use it to find that sweet spot for production costs. It's used in agriculture to maximize crop yields, and in physics to understand waves and vibrations. This math is quietly running in the background of our entire world.
So the ultimate takeaway here is this, that strange little number I and the complex roots it helps us find aren't just some abstract curiosity for mathematicians. They are the essential ingredient that allows our mathematical models to be complete, accurate, and truly predictive of how the world actually works.
And that leaves us with a final question for you to think about. Whether it's in your job, your personal finances, or maybe a hobby you're really passionate about, what complex system could you model, understand, and maybe even optimize now that you have the complete toolkit? Thanks for watching. All right, welcome to The Explainer. Today, you and I are going to become master locksmiths. We're going to learn how to pick these tricky algebraic locks on complex polynomials and, reveal the secrets that are hidden right inside. All right, let's just jump right in. Here's what we've got on tap for today. We'll start by figuring out what these puzzle boxes even are. Then we'll grab a key you probably already know how to use, and then we'll get into the master techniques to crack pretty much any lock that comes our way. So first things first. Before we start picking locks, we've got to understand what we're up against, right? What exactly is this locked box we're trying to open?
Okay, so you look at something like this, and yeah, it can look pretty intimidating. It's like staring at some super complex lock, but where's the keyhole? Where do you even begin?
And this is where the real magic happens. The key, no pun intended, is to completely flip how you think about this. We're not just solving for X in the traditional sense, nope. We're on a mission. We're detectives trying to find the smaller, simpler pieces, the factors, that were multiplied together to build this thing in the first place.
So let's break this down. The really crucial piece of information here is something called the degree. That's just the highest exponent you see on the variable. For the puzzle we're looking at, it's that little 3 on the x cubed. And that degree is a massive clue. Thanks to something called the fundamental theorem of algebra, it tells us the maximum number of keys or roots we're looking for. In this case, 3. We need to find up to 3 keys to completely unlock this box. Okay, so let's start by grabbing a tool that should feel pretty familiar. By warming up with a key most of us have used before, we'll get our confidence up for the trickier locks that are coming.
Right. This is our bread and butter, the foundational skill, and it's a super reliable 3-step process. First, you're going to find 2 numbers that multiply to whatever A times C is. Then you have to make sure those exact same 2 numbers add up to B, that middle term. Once you've got them, you just rewrite the expression and factor by grouping. Boom, you found your keys. And here's what that looks like in action. See? What started as this jumble of terms is actually just two simple little packages, 2x plus 3 and x plus 2, multiplied together. We found the keys. We opened the box.
Okay, warm-up's over. Now it's time for the master keys. Seriously, these next two theorems are the most powerful tools in our entire kit. This is how we're going to tackle the big ones, like those cubic and quartic polynomials. Okay, so on one side you have the remainder theorem. All it says is that if you divide a polynomial by, say, x minus c, the little bit that's left over, the remainder, is the exact same thing you'd get if you just plugged c into the function, f of c. Kinda neat. But now look at the other side. This is where it gets really exciting. The factor theorem is just a special case of this. It says, what if that remainder f of c happens to be 0? Well, if the remainder is 0, that means x minus c divides in perfectly. It's not just some random divisor, it's a factor. It's one of the keys we've been looking for.
This right here, this is the core idea. It's basically a simple test. You pick a number, c, you plug it into your polynomial, and if the whole thing crunches down to 0, then bam, you just found a factor, x minus c. This is literally our lock-picking tool. It lets us try the keys.
All right, so this is great. We know how to test a key if we have one. But where do we get the keys to test in the first place? I mean, we can't just guess random numbers all day, right? That would take forever. Well, this next theorem, it gives us the blueprint.
And this theorem is an absolute game changer. Instead of staring at an infinite number of possibilities, the rational zero theorem hands us a nice, short, specific list of potential keys. It takes an impossible search and turns it into a totally manageable systematic process. So how does this recipe work? It's actually really clever and pretty straightforward when you think about it. The theorem tells us to list all the factors of that constant term at the end. We'll call those p. Then list all the factors of the leading coefficient at the front. We'll call those q. The complete list of all possible rational keys will be every single possible fraction you can make, plus or minus p over q. Okay, let's put this into practice with our puzzle box, x cubed minus 2x squared minus 5x plus 6. So our constant term, p, is that 6 on the end, so its factors are pretty simple, plus or minus 1, 2, 3, and 6. Now for q, the leading coefficient, that's the invisible 1 in front of the x cubed. Well, its only factors are plus or minus 1. Super easy. Okay, now for the final step, we create all the p over q fractions. But wait, since our q is just 1, this gets really simple. Our whole list is just the factors of p. And that's it. This is our key ring. We now know with 100% certainty that if this polynomial has any nice, simple, rational roots, they have to be on this list of 8 numbers. No more guesswork.
All right, the moment of truth. It is time for the final test. We've got our locked box from the very beginning. We've got our shiny new key ring. Let's put these tools to work and crack this thing open, step by step.
So where do we start? Let's just try the easiest key on the ring, x equals 1. We're going to plug that 1 into our function everywhere we see an x. So f of 1 equals 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. Let's do the math. That's 1 minus 2 minus 5 plus 6. And when you add all that up, what do you get? You get 0. It worked. First try. How about that? Okay, this is the crucial part. Since f of 1 equals 0, our magic factor theorem guarantees that x minus 1 is a factor. So we found one key. To see what's left of the lock, we need to divide it out. You can use polynomial long division or, my favorite, synthetic division. When you do that division, what pops out is a much simpler problem, a quadratic, x squared minus x minus 6. We've basically unlocked the first tumbler, and now we're left with a simple lock we already know how to pick. And there it is, the final step. We just factor that little quadratic that's left over, x squared minus x minus 6. We're just looking for two numbers that multiply to negative 6 and add to negative 1. And of course, that's negative 3 and positive 2. So it breaks down into x minus 3 and x plus 2. And just like that, we're done. We've used our theorems step by step to find all 3 keys, x minus 1, x minus 3, and x plus 2. And we have completely cracked open our puzzle box. So why? Why do we do all this? I mean, it's a pretty cool puzzle, for sure, but what's the point? Why spend time learning how to unlock these algebraic boxes? Well, let's connect this to the real world. Okay, here's a really direct and powerful application. Imagine a company has a big, complicated polynomial function that models its profit. If they want to find their break-even points, the point where profit is exactly 0, What are they doing? They're finding the roots. Finding these factors tells them exactly how many widgets they need to sell to stop losing money and finally start turning a profit. These aren't just abstract numbers. This is critical information for any business. And that really brings us to the bigger picture. This whole technique, fundamentally, is about taking something that looks messy and complex and breaking it down into its simple, core components. It really makes you wonder, doesn't it? What other complex systems out there, maybe in engineering or biology or even economics, could be better understood if we could just find the right hidden factors to unlock them?
All right, let's get right into it. We're all so used to just grabbing a graphing calculator to see what a function looks like, right? But what if you couldn't? What if you had to predict the wild, winding shape of a complicated polynomial graph with just your brain and a pencil? Well, today, that's exactly what we're going to learn how to do. I mean, take a look at this thing. It's got all these peaks and valleys. It's crossing the axis all over the place. It looks like total chaos. How in the world are we supposed to know it's going to wiggle in this exact way just by looking at an equation? It feels impossible, I know, but I promise you, it's really not. You see, hidden underneath all that complexity is a really beautiful, predictable logic. There's a method, a system of clues that, when you put them all together, reveals the graph's true shape. Think of us as detectives for functions, and today we are about to crack this case wide open. So, here's our 4-step game plan. First, we're going to zoom out and get the big picture. Think of it like a roller coaster. Then, we'll zoom in and find the key landmarks on our map. After that, we'll look at bounces versus crossings, a crucial detail. And finally, we'll put all our clues together and sketch the final path. Sounds good? Let's do it. First up, the roller coaster's big picture. This is all about a concept called end behavior. So before we get lost in all the little wiggles and turns in the middle of the graph, we need to know 2 things. Where is this graph coming from, way over on the far left, and where is it going, way over on the far right? And that roller coaster analogy is just perfect. You know, the most powerful part of any polynomial, its leading term, is like the giant engine that dictates the whole ride's direction. It tells you if the roller coaster starts low and ends high, or maybe starts high and ends low. This is our first and honestly our biggest clue. And check this out, there are only 4 possible scenarios, and it all comes down to 2 super simple questions. First, is the highest exponent, the degree, an odd number or an even number? If it's odd, the ends of your graph point in opposite directions. If it's even, they point in the same direction. Easy. Second question, is the number out front, the leading coefficient, positive or negative? If it's positive, the right side of your graph will always end up pointing upwards. If it's negative, the right side points down. That's it. You combine those 2 simple rules and you have your answer every single time. So, let's try it with our example polynomial. The highest power is 3, which is obviously an odd number. So boom, we know the ends go in opposite directions. The leading coefficient is a positive 2. That positive sign tells us the graph is going to end by going up on the right. And since we know the ends are opposite, well, it must be starting by coming from down on the left. See? Starts down, ends up. First piece of the puzzle, locked in. All right, let's move on to our next big step, finding the key landmarks. We know where our roller coaster starts and ends, but now we need to know where it crosses the ground, the x-axis. These crossing points, which we call zeros or roots, are basically the most important landmarks on our map. But how do we find them? I mean, we could just guess random numbers all day, but that's not exactly a great strategy. Instead, we use this amazing tool called the rational zero theorem. Now, it sounds fancy, but here's what it does. It gives you a complete list of every possible rational number that could be a zero. It basically takes a giant haystack of infinite possibilities and shrinks it down to a tiny, manageable pile so we can actually find the needles. Let's walk through it. For our equation, the theorem tells us to take all the factors of the last number, the constant term, -6, and divide them by all the factors of the first number, the leading coefficient, 2. This gives us our list of possible zeros, plus or minus 1, 2, 3, 6, and also the fractions 1/2 and 3/2. Now we just have to test them. Let's try x equals -1. We can use a fast process called synthetic division to check. And when we run the numbers, we get a remainder of 0. That's the jackpot. That confirms that x equals -1 is a 0. Even better, the result of that division gives us what's left over, a much simpler quadratic equation, 2x squared plus x minus 6. And that's something we can easily factor into 2x minus 3 and x plus 2.
And just like that, by solving those two little factors, we find all our landmarks. From the x plus 2 part, we get x equals negative 2. We already found x equals negative 1. And from 2x minus 3, we get x equals 1.5. These three numbers are the exact precise locations where our graph is going to cross the x-axis. Our map is really starting to fill in now.
Okay, but hold on. Here's a small but incredibly important detail. Just knowing where the graph hits the axis isn't the full story. We also need to know how it behaves when it gets there. Does it slice right through the x-axis, or does it just kind of touch it and turn back around? This is all decided by something called multiplicity.
And multiplicity is just a fancy word for how many times does a zero show up as a factor. It's simple. If a zero has an odd multiplicity, like 1 or 3 or 5, the graph will cross straight through the axis at that point. But if it has an even multiplicity, like 2 or 4, the graph won't cross. It'll just come down, touch the axis, and bounce right back off, kind of like how a parabola hits its bottom point.
Now, if we look at our example, the factored form was x plus 2 times x plus 1 times 2x minus 3. See how each of those factors is just there once? They're all raised to the invisible power of 1. And since 1 is an odd number, every single one of our zeros has an odd multiplicity. So no bouncing for our graph. It's going to cross the x-axis cleanly at all three of our landmark points.
And that, my friends, brings us to the grand finale, sketching the final path. We have gathered all of our clues. We know the end behavior, we know the exact locations of our zeros, and we know exactly what the graph does at those zeros. It is time to connect the dots and bring this picture to life.
But wait, let's grab one more super easy landmark first, the y-intercept. This is just where the graph crosses the vertical y-axis. And to find it, all you have to do is plug in x equals 0 into the function. When you do that, all the terms with an x just vanish, and you're left with that constant term at the end, which for us is negative 6. So we know for sure our graph has to pass through the point 0, negative 6.
Now, to be absolutely sure we get the shape right between our landmarks, we can quickly test the intervals. Our zeros at negative 2, negative 1, and 1.5 chop the x-axis up into 4 different zones. All we do is pick one test number in each zone to see if the graph is above the axis, which is positive, or below it, which is negative. For instance, in the zone between negative 1 and 1.5, we could test x equals 0. We already did that. We got negative 6, which is negative. This table shows the full result, and it confirms the up and down path of our graph. It goes from negative to positive, then back to negative, and finally to positive again.
So here it is, our final detective's checklist. We know it starts down on the left and ends up on the right. We know it crosses the x-axis at negative 2, negative 1, and 1.5. We know it passes through the y-axis at negative 6, and we know the exact pattern of its journey. Negative, then positive, then negative, then positive. We literally have everything we need.
So now, we just play connect the dots, making sure we follow all our rules. We start from the bottom left because that's our end behavior. The curve comes up and crosses the axis at our first zero, negative 2. Now we're in positive territory, above the axis, but it has to curve back down to cross again at negative 1. It keeps going down, passes through our y-intercept at negative 6, finds its lowest point somewhere down there, and then turns back up to cross the axis for the last time at 1.5 before it shoots off toward infinity on the top right. And there's our sketch.
And that leads to one final thought. Take a look at this. Imagine a graph that's almost identical to the one we just drew, but at one of the zeros, instead of crossing, it just touches the axis and bounces off. What single tiny change in the equation could cause that big a difference in the picture? Well, if you're thinking it has something to do with giving that zero an even multiplicity, you are absolutely right. And that's the real power of learning this stuff. It gives you a deep intuition for how the language of algebra actually creates the beautiful geometry of these graphs.